So our next speaker is Dr. Adam Miller, and he is going to be talking to us about operational T&E of AI-supported data integration, fusion, and analysis systems. So with that, I will turn it over to you, and it should pop up here. Yep, there we go.
Oh, great. Great, thank you, Brianna. And good morning, everyone. So I have just a very simple outline today. So I'm going to introduce the idea of AI-supported data integration systems. I'm going to talk about some of the challenges that they pose for operational test and evaluation. And then hopefully I'll be able to present to you some strategies for overcoming these challenges, including an example evaluation. Okay, so what do I mean when I say data integration system? So data integration is exactly what it sounds like, right? You're going to grab data from a whole bunch of different sources, a whole bunch of different types of data. You're going to pull it in, you're going to format it, you're going to fuse it into the sort of underlying entities that those data points refer to, and then you're going to create a database that users are able to interact with in order to generate analyses. And my personal favorite example of a data integration system is Google Maps. So Google Maps is something that most people are familiar with. You probably don't think about it day to day, but it actually does this sort of extraordinary job integrating information, all sorts of data. So you have sort of the satellite images from Google Earth. You have these street view cars, including kind of the backpacks that people wear around and go on hikes and stuff, that produces all these sorts of images. You also have just a ton of user data, right? We're walking around with cell phones all the time. Your GPS provides sort of live traffic information to Google Maps, but also users are providing feedback, right? If you go to Chipotle and you think it's kind of a 1 out of 5 stars, you'll write that down. Maybe you have a comment. All of this information has to come in whatever format it arrives, and then Google Maps will sort of format it into these simple images and text and stars that you see on their website, right? But then they do this really important trick. So they're going to fuse elements. They have this big stack of formatted data, right? But all of this data doesn't belong to just one thing. It belongs to all these different locations all around the world. And they have to look at this stack of data and say, which things in this pile all belong to, for example, the Pentagon, right? And so they'll form these sort of web pages that you're familiar with seeing when you use Google Maps. So you have the images of the Pentagon Street View, you got its location, user feedback, all the sorts of reviews, things like the phone number that might have been scraped from a website, and they create this sort of entity. We have another one here for IDA, and with all of these entities together, you end up with something akin to kind of a living database. This is what you guys are probably familiar with interacting with, right? And this is when you and I come in. We're users, and we're going to interact with this database in order to produce, what I might generously describe as some sort of an analysis, okay? So you come in with a question in mind. Maybe you want to put together kind of the perfect tour of DC or whatever it is, and you're going to approach, and this is also a really good example for how users might interact with AI when they're engaging with a database, right? So you have some locations in mind. Maybe you're visiting Washington, D.C. for the first time, so you really want to see IDA, of course, and so you kind of list IDA, and then the AI will recommend some other kind of related locations, right? So and you look at those and you have to make decisions. Is this something I also want to see, or maybe I'm not so interested in the Capitol, for example? And so you're going to put together all of these locations, and then of course Google Maps, maybe what it's most famous for is it will help produce some sort of candidate routes. So there are like literally an infinite number of ways you can get between all these different locations, but Google will sort of run the numbers and it will give you a few candidate options, and then you can select between those candidates based on your own personal criteria, right? So this is a good example of user and AI collaboration to produce some sort of an analysis output. Okay, so if that's Google Maps as an example, this is kind of the notional framework, the more general framework I'm going to be using for talking about AI-supported data integration systems. It has a lot of the same components as the Google Maps example, so you're still starting with raw data. You have to extract the important elements of that data and format it for a database. You're going to fuse it according to the underlying entities like IDA or the Pentagon that it belongs to. And then you're going to produce an analysis. I am, however, injecting some additional users here which may exist in systems you guys are looking at, and I've just kind of named them in sort of typical ways. But you have an engineer who's working with AI to perform this process, right? Each of these processes could be thought of as kind of a user and AI supported like data transformation, right? And it's a series of data transformations that results in this analysis. And for some systems, you might also have kind of a consumer, right? Sometimes there's an individual who's actually going to be receiving this information. For example, if you have a relative who came into town and you're going to present them with your perfect tour of DC, they might sort of evaluate your analysis. They might act on that analysis. Okay, so let's talk a little bit about the challenges that are posed by these sorts of systems for test and evaluation. Preview it here, but give myself a drink. Okay, so from my perspective, the biggest challenge for these sorts of tests is the data. Now, we all are probably very aware that data plays an important role in training systems, right? So the training data is how systems develop their capabilities, but it's in operational test and evaluation that you're going to find out if those capabilities actually exist and can support sort of an operational mission. And so, of course, you're going to want to include a lot of data that is very representative of the kinds of things that the system would see in the field. And this includes kind of obvious things, like you'd like to have all the different types of sensors and inputs that the system is going to receive. You want to have all the different types of entities. So, we talked about locations, but there may also be kind of people or vehicles, all these different things that the data need to be fused into. And then there's kind of lower level things that you need to make sure you include. So operational data tends to be very messy, right? And I've kind of included an example here, which is we're talking about duplicate records or redundant records. So think of it like this. So if the shopping center next door with Target were to one day suddenly list IDA as belonging within that shopping center, it's important that Google Maps doesn't suddenly, decide that there's a second IDA located just a couple blocks away. It needs to realize that that's referring to the exact same IDA that it already has a record for, and make sure that it fuses those together. Sometimes the information doesn't arrive to your system directly, but it will get passed through some sort of a database that you have a subscription to, and you need to be able to deal with those sort of redundancies. But this is an example, a single example of kind of how you need to make sure that you understand the kinds of complexities that exist in your operational data and make sure that you include those in your test data. The second challenge that I see is how are you going to grade the responses of your system, right? So I talked about this really neat trick that Google Maps does where it has this pile of formatted data, and it looks through and it finds the things that are referring to the same underlying entity. And so, you have this kind of information maybe that's scraped from a website, an image of IDA, the satellite image of IDA, and somehow from the pile you need to realize that all of these and only these are referring to IDA, and you need to fuse those appropriately. And this, of course, seems like a very easy task for us because we all know a little bit about IDA. Also didn't include anything else except for those three images. But we're not really building these systems generally for users who already have all of the answers, right? Typically, if you are building these systems, it's because you want to learn something. You want to discover sort of these underlying entities and the information about them. And so if you don't know the ground truth, how are you going to grade the responses of your system, the sort of predictions that it's making? That's another challenge. And then the third one here, third panel, is just a question about the AI contribution. So you might remember from sort of your time in primary school, if you ever do a group project, there often are some kids who are real go-getters and then some other kids who aren't really go-getters. And it's very difficult for the teacher maybe to evaluate who was contributing what to the project if all they ever see is the end result, right? No matter how good that result is, it always could have been the case that some of those students might have done even better if they hadn't been pulled down by some of the other ones, or vice versa. And so if you're interested in evaluating how your AI is making a contribution to your system, we're going to talk a little bit about that in a bit too. And then just three more challenges. These are all sort of related to the overarching idea of evaluating your system across the operational envelope, right? So a big idea here with evaluating AI is that it can be very difficult to predict how it's going to respond, especially to very rare inputs that may not have been included in the training set, may not even have been included in the testing set. So this is sort of a famous or infamous example of when Apple Maps was new. So I'm not as big of a fan of Apple Maps. And it was working out some bugs, and it was asked, how do you get from sort of this location on the mainland out to this island? And it clearly hadn't been trained on that sort of information because the suggestion, what it came up with was, just drive straight, right? Go right through the ocean there. And that's not a very good strategy. And this is, of course, predicting its performance to rare inputs is related to sort of the second challenge here, which is, we often don't know sort of the underlying solution that the AI has settled on when it's trained on the test set, right? So you give it this test set, it learns that it performs well. With a lot of systems, you sort of come away with an intuition, outside of data integration. You come away with an intuition of this is how the system operates, right? And so you can make kind of intuitive guesses about how it might respond to other stimuli that you haven't tested it with. And this is essential because, almost never are you going to be able to test a system against everything it ever faces. But in these cases, if you don't really have access to the idea of the solution, there's always this risk that the system has learned something quirky, right? One example of this is overfitting. If it's just sort of learned the particulars of your training set, it's learned the responses to those training data that count as successes, you can end up with an overfitted system where even if you then later present it with data that kind of fall within the general trend, if it doesn't have the right solution, it might treat those as rare inputs and act sort of strangely to those. And then the third and last problem I'm going to talk about here is that models can change over testing, right? So as testers, and I saw a lot of hands go up in the last presentation, so we have a lot of people here with test experience, we're sort of familiar with this idea of a dynamic testing environment. So you have users who are sometimes interacting with other users, and they can change each other's behavior, they can change the environment, they can respond to the environment. If you add AI into this mix, you're increasing this sort of dynamic environment. You have an AI interacting with a user, you can get adaptation there. You can learn how to use Netflix better, but Netflix can also learn you better. It can start making better predictions. And of course, if you have an AI whose recommendations are being acted upon in a way that they change the environment, you can see this here as well. Now, the key I just want to take away from here is that if systems are going to change over testing, you need to design your tests in a way that allows them to change. You can't just reset after every run, for example. Otherwise, you may not see how the system evolves, and you may not be able to observe how it would respond in the field. Okay, so those are the problems. Let's talk a little bit about some solutions. So I said test data is one of the ones that's most important to me, so let's just talk about test data. So with most systems, if you have access to actual operational data and you can feed that to your system, you're in a really good place, right? That's often very difficult to do. But with data integration systems, having operational data is not enough. You also need to know something about kind of the underlying reality of the world that led those sensors to send you this information, because that's what you're trying to predict. And if you don't have that ground truth information, it's going to be very difficult for you to evaluate or grade the guesses that your system is making about the underlying truth, right? And so you end up with this sort of tension here, where you really want to give operationally realistic data, but you don't have ground truth information about that, so you won't be able to grade the system's responses. And so on the other side, you have this kind of tension between operational and data that you maybe generated yourself, maybe with a simulation, right? So if you made the data, you know exactly how the system should be responding to it, which is really great, but at least for grading. But of course, if it's synthetic data, if you generated it, then it's never really going to be fully operational, right? It's very difficult to capture all of the sort of nuances of operational data in data that you've sort of created in a lab. And so you're stuck with this sort of tension here. You're in these yellow boxes, but you want to be in this green box. So how can you improve this? Well, one obvious candidate is to try to drag your synthetic data to the right here, right? Can you improve the operational realism of your synthetic data? That's a noble cause. I think everyone agrees with that. That would be really great. It's really hard to do, and generally, you might not have a lot of control over that. And so another option is to try to drag the operational data up to this green. And so I'm calling this approximating truth for your operational data. So if you're going to have operational data, you have the opportunity to feed that to your system. You just need to come up with some sort of an answer key, and we're going to talk about that on the next slide. Not a perfect solution, but I think a workable one. And then, of course, if you have the option, and this seems to be the answer for all of these sorts of straw men. But if you have the option, combining both of these is a really great choice, right? If you can give it operational data, see if it does weird stuff with the real data, but then also grade it against synthetic data that you trust, obviously that would be a best case scenario. Not always possible. Okay, so I talked about approximating ground truth. What do I mean by that? So with these systems, data integration systems, you often have a ton of data, real operational data available. That's kind of the blessing of these systems, right? You have all this data coming in, and in fact, it's because you have all this data and you need to process it that you're developing this system in the first place. And so maybe the most obvious approach here would just be to grab a batch of that data as it arrives, and then feed it to your system. So that's what I'm trying to visualize here. So you have kind of all this data arriving all of the time. Oh, shoot. Okay, you guys can't see, but it's a really beautiful image that someone made where you just have sort of the data pipe. Anyway, so the data's coming in all the time, right? And think of it as being kind of time-stamped, and so this isn't a complicated idea, but it's being time-stamped, and it's arriving somewhere between, right now in the present all the way back into the past. And so what you might want to do is just grab a batch of data, grab sort of a time window or a slice out of this timeline with all the data that arrived in this period, for example, and that would be your test data. Now you're just going to try to feed that to your system. But of course, if you feed that to your system without an answer key, you're going to get responses back, and you're going to be like, I don't really know if that's good or if that's acceptable. And so what we recommend as kind of a workaround is to first hand that data to an expert, right? Hand it to an expert who, with the benefit of hindsight, especially if you've chosen this from pretty far back, right? You have this SME who's now seen all this, so they're kind of like a time traveler. They've come back, and they're sitting here, and they're going to be able to tell you a little bit about the state of the world at this point in time that led to this data. And so then you can feed that real operational data to your system and then grade its responses according to this time-traveling SME, right? I hasten to add, of course, that this is not a perfect solution. SMEs can be wrong, and that's something you're going to need to keep in mind, and we'll talk about a little bit later. Okay, so you have this data, you fed it to your system, you have an answer key, and you want to do an evaluation. What does that look like? Okay, so I'm going to keep this super, super high level because I don't think the details maybe are really all that important for this particular discussion, but I'll just keeping it simple, we'll say, if you have access to ground truth data, then your evaluation will be pretty straightforward, right? So imagine that you have a categorical variable. If your system's outputting categorical variables, so Google Maps, finds a location, and it has to decide whether it's a store or if it's a restaurant, okay? If you have ground truth available, this is pretty straightforward. So you're just going to ask the system, what do you think this thing is? You're going to look at ground truth, and you're going to see if they agree. The underlying idea here is a confusion matrix, which maybe I imagine people are pretty familiar with. But, on the surface, a pretty straightforward example. The details of this are a little more complicated, and so if you find yourself in this spot, you're going to have to think pretty hard about what agreement or good or acceptable agreement means to you. And your particular system, but the kind of overview here is pretty simple. On the other hand, if you have a system that's outputting sort of a continuous response, so for Google Maps, an example would be the predictions it makes about how long it will take you to get to your location, right? So if Google Maps makes some great discovery that it takes longer, for example, to get someplace when it's further away, it'll model sort of the relationship between those two things, and that model itself constitutes a prediction about how long it thinks it should take when two things are a certain distance apart, right? Of course, then, as operational testing goes, you get in your car, you drive out there, and then maybe it predicted it would take 17 minutes, it took you 19 minutes. That's error, right? That's error. Okay, if you do not have ground truth, things get a little trickier, right? And this is going to be, I think, a pretty common situation people find themselves in. So if you do not have ground truth, or if you additionally, you have ground truth, but additionally you'd like to kind of contextualize the performance of your system in terms of human performance, one approach is to use inter-rater agreement here. So the conceit of inter-rater agreement is that humans don't always agree with one another, and experts do not always agree with one another. And if you can find sort of the distribution of that disagreement between experts, you can use it to quantify, let's say, you can use it to ask, do the experts agree with each other to a similar degree that they agree with the SME? Or do they disagree to each other to a similar degree that they disagree, with the AI? You're trying to determine if the AI is essentially just one of the SMEs, right? Do they all kind of agree and disagree at the same rate? This is going to give you a relative measure of performance. That might be what you're looking for, but importantly, it's not the same as sort of an absolute measure of performance. Whether or not, it won't tell you absolutely whether the system is correct. That's going to depend on whether the SMEs were correct and whether they agree. But this might be what you're looking for anyway. Importantly, obviously, I just mentioned that SMEs don't always agree. So again, that's something, or aren't always right. So that's something to keep in mind.
Can't you ask that AI, 10,000 times and then get the distribution and see the full distribution against where the SME distribution would be?
So if you have an AI system where you put in the same responses and you get out different answers, then you could plausibly have a distribution. The underlying idea would be the same. Okay, we also think that it's important, if you're going to do a good evaluation, that you include an evaluation of HSI. I'm going to talk more about this in the details in a couple slides from now, I think. But I just want to call out two really important HSI concepts if you're working with AI, and those are calibrated trust and also utilization behavior. So it's really important that your users understand the system well enough to know the conditions under which it works well and the conditions under which it doesn't. So we keep talking about Google Maps examples. So Google Maps, if you click on a location on the map, it will tell you, it pulls up that little entity box that we described, and it will tell you the hours that it's open for that day. And I use this all the time. I think it's really valuable. I think it's really accurate. Except on holidays. If you've ever tried using this on a holiday, you'll know you show up at CVS and you need Pepto-Bismol or whatever it is going on, and the store's not open, right? And so I've learned over time not to trust this. You don't use it on a holiday. If it's a holiday, you just say, that's not worth my time, that's not garbage. And what I'll end up doing is I will call ahead. I'll just call on my own, right? And so two things here, if you're going to measure this, right? You want to see human trust. Human trust should be high in the Google Maps hours, off holidays, and my trust is very low on holidays, right? So it should correlate with the accuracy of the system. And then, of course, you have utilization behavior. This is me, no longer using it, and I'll now call instead. This utilization can have two sides. So one is you're sort of accepting the information that's being given to you, or you're not. And the other side of this, which is being shown here, is intervention behavior. So for some systems, you're asking humans to intervene. And the important thing here, as far as utilization behavior goes, is you want to see them intervening in cases where the system is going to perform poorly, but not intervening in situations where the system is actually going to perform well. Okay, finally we're getting at this sort of example evaluation. So this is the same notional framework I showed before. I've kind of changed the language here. It's now this curated historical scenario or whatever, but the raw data is coming in, it's being extracted, fused or correlated, those are synonyms, and then you're producing an analysis for a consumer. Each of these, again, it's a user plus AI sort of guided data transformation. Let's talk about the users first. So we're recommending a triangulation approach. So we're going to use surveys, interviews, and behavior to really pin down the HSI concepts that we're interested in. And as far as HSI concepts, we recommend playing the hits. So go ahead and measure usability. That's how usable sort of the interfaces are for your users as they're performing these transformations. Also workload, right? What's their level of workload during this process? I have timeliness up here. So for these systems, sometimes even accurate analyses are useless if they take too long to arrive. And so how long does it take a user to make this transformation after they receive kind of their local input? And then we just talked about calibrated trust and utilization. For some systems, I mentioned a consumer is important. I find that these tend to be kind of experts in looking at these analyses. So at least for superficial details, their approval might tell you whether it contains the kinds of information they're looking for, if it's in the right format that works for them. But of course, we want to actually evaluate the products as well. So we have each of these along the way, and we recommend looking at accuracy. We just talked about this. So accuracy in these cases might be a comparison to ground truth if you have it. Alternatively, it might be a relative comparison, right, to answer keys that are generated by SMEs. And then if your consumer is making some sort of decision with the analysis, it might be useful, because this is kind of the ultimate operational output of this system, right? It might be useful to evaluate sort of the accuracy or the outcomes of the decisions that the consumer makes based on the analysis that's produced by your system. Okay. So I think this is pretty good. I mean, you guys can decide, but I think this is a pretty thorough evaluation. One thing it doesn't do, which you might be interested in, is determines sort of the contribution of the AI, right? We talked about this during the challenges that these systems pose. So no matter how good this analysis is, it could always have been the case that it would have been better, or that the users would have got it out faster if these AI hadn't been, making a bunch of terrible suggestions that the users had to weed through or something. And so if it is important to you to evaluate the specific contribution that's being made by the AI, we recommend a comparison approach. And so I have shown up here the system with the AI and here's a comparison system. And so one possibility is that the comparison system is the same system, but with the AI features disabled or turned off. Alternatively, it may be the case that this is the new implementation of your AI or the newest version of your AI, and this would be an older version. But in either case, the comparison approach is, I think, a really powerful tool. So it allows you to sort of evaluate the HSI concepts that you're interested in. What's the workload of the user with and without HSI at every single step? Also, the quality of the data products that those users and AI are producing. Is that higher at each stage than versus the system with, for example, the old AI? This is also a very flexible approach, so I've shown kind of the whole test here. If you're making a big change to your AI, you're upgrading the AI early on, you might want to look at this full test because it will let you see kind of how the effects of a change early on ripple through the pipeline. Of course, if you're making a much smaller change, maybe right here, you're just upgrading a little bit in the middle, you might be able to get away with a more circumscribed test. You could just scrounge up some existing or extracted data from a prior test, feed that to the manager plus the new AI or the manager with the old AI, and then evaluate their correlated or their data outputs, local data outputs. And so it's really flexible, and it's sort of up to you based on your needs. Okay, I already got my call for time, so I'm just going to hit 2 slides here about test design. We just have a couple ideas. So the first one is operational factors. So obviously we talked a lot about the challenges of evaluating a system across or over the entire operational framework. When it comes time to choose operational factors, sort of the important thing to realize is that operational factors here are referring to the test data you're delivering to your system, right? When you have that sort of timeline and you're going back and you're grabbing slices of test data, you want to do that intentionally so that you grab data that represents or from all over the operational envelope. And so the things we're going to stress on here are things I've already sort of mentioned. You want to make sure that you have all the different types of data sources. Maybe your system's better at handling some sources than others. Entity types. Google Maps deals with locations, but I mentioned that your system might do other things like people or vehicles. Make sure the system performs well across all entity types. Duplicate records here is just a stand-in, again, for this idea of the messiness of real operational data. It'd be nice if you could evaluate your system over sort of an axis of this sort of messiness, if you will, right? It may be the case that your system performs well up to a certain point, and then its performance starts to dip. Geographical regions for these systems tends to be more of an umbrella concept here, right? So the data sources, the types of inputs you're going to get, the types of entities you might see, they might differ in Asia, for example, than in Europe. And then we also think it's important to evaluate the system over network domains and sort of security policies. And then lastly here, as far as test design goes, so sizing tests is a really challenging question to speak specifically about in this kind of notional framework. But I can say that it hews to kind of your intuitions as testers that, more familiar systems require less testing than unfamiliar systems. So if the system or the mission capability or AI is very novel, if the magnitude or complexity of the AI's contribution is very high, you'd expect that in those situations you would require more testing. On the other hand, if you know that it was trained, that the models were trained very well with very realistic operational data, if you have access to ground truth, so you have a good understanding of what right should look like, or of course if you've done prior testing, right? Under these conditions, you would perhaps need less testing. And then just a summary of everything I touched on here. So we think these sort of data integration systems are really good candidates for AI, and so we anticipate that we're going to see more evaluations like this in the future. When you're doing these evaluations, it's important to of course, measure sort of the model performance and the types of data products that are being produced. But we also encourage you to measure HSI of the users who are doing the generation of these data products, or at least overseeing it. If you are interested in evaluating the specific contribution of the AI to your system, a between systems comparison approach might be useful for you. And then finally, of course, when you're trying to characterize performance over the operational space, you need to choose operational factors that describe well sort of the operational inputs it would see in the field. Anyway, thank you guys for your time. Sure.
How do you see this playing out for systems that have been deployed, probably the testing community? Have
you identified critical links or critical responsibilities that must be ongoing through the life cycle of the project?
I have not. Yeah, I mean, how to continue evaluating systems that may be continuing to learn over the long term is a really important and difficult question, and I do not have answers for that right now. No. Good.
I don't know if anybody has.